Hello, I'm Ray. This is the topic of my presentation. As online learning grows, we collect more student behavior data over time. This data helps us understand learning patterns and find students who need help early. But traditional models use only simple data and can't explain their results well. So in this study, I compare two deep learning models. One DCNN, which is good for early multi-class prediction. ATN, which uses attention to show what affects the result. My goal is to find a model that is both accurate and easy to understand for better use in real classrooms. This study uses a neural network to predict student performance in four categories: distinction, pass, fail, and withdrawn. It uses early data from the online course like student background, test results, and click behavior. The model uses a 1D CNN and gets better results than other models like Random Forest and LSTM. Even with only 20% of the course data, it can predict well. This helps give early warning for students who may fail or drop out. This model uses three types of student data: demographics, registration info, and VLE click behavior. First, it merges and processes the data. Then it creates features like click count and registration days and standardizes them using Z-score. The processed data goes into a 1D CNN model to learn patterns over time. Finally, the model predicts student performance in four categories: distinction, pass, fail, or withdrawn. The proposed prediction system begins by loading the OULA dataset, which includes demographic information, assessment scores, and clickstream behavior. These data are organized across 7 CSV tables, including student, info, registration, and VLE. Next, the system performs feature engineering to generate meaningful variables such as total click count, total registration days, and average assessment weight. Missing values are filled, and the data are normalized using Z-score standardization. After pre-processing, the structured data are fed into a 1D CNN model. This model learns temporal patterns across the time dimension to classify student performance into four categories: distinction, pass, fail, and withdrawn. Finally, the predictions are used to support early intervention strategies, allowing educators to identify at-risk students in the early stages of a course and offer timely support. This study uses the OULA dataset from the UK Open University, containing data from 32,593 students. It includes demographics, registration records, assessment results, and VLE (Virtual Learning Environment) interaction logs. The dataset is structured across 7 CSV tables. The target labels include distinction, pass, fail, and withdrawn, making it a multi-class classification task. The model uses a time-based progressive prediction strategy predicting performance at multiple stages of the course. This setup simulates real-world early warning conditions. To maintain fairness and class balance, stratified cross-validation is applied. The proposed 1D CNN model outperformed all baseline models in predicting student performance. It achieved an average accuracy of 91.8% when using just 20% of course data and exceeded 95% accuracy with 50% of course data. Compared to models such as ANLSTM, Random Forest, and DFFNN, The 1D CNN consistently delivered better precision and F1 scores across all evaluation phases. This study introduces ATTEN-ANN, an attention-based artificial neural network designed to predict student performance based on weekly learning activity data. The model uses attention mechanism in two dimensions, time and features. The model was evaluated using LMS logs from Japanese university courses. Compared to traditional deep learning models, ATTEN-ANN demonstrated improved prediction performance and offered much better interpretability. Additionally, the attention weights allow instructors to visualize which lectures or activities contribute most to student outcomes, making the model useful for early intervention. The ATTEN-ANN model is designed to analyze weekly learning behaviors and identify at-risk students using a dual attention mechanism. It processes weekly activity data from platforms like Moodle and Bookroll, transforming these logs into active learner point vectors. The system applies time-based attention to highlight important weeks, and feature-based attention to focus on the most influential learning actions. By combining these attention weights, the model produces a binary prediction, whether a student is at risk or not at risk. It also provides visualizations to help instructors understand which actions contributed most to the result. The attention model predicts at-risk students using weekly learning logs from LMS and eBooks. These logs are converted into ALP feature vectors and encoded by an RNN. The model applies attention over time and features to highlight important weeks and behaviors. It then combines the information and outputs a binary prediction with attention maps to support interpretation. This study uses data from two university courses, a 7-week programming course and a 13-week signal processing course, collected from 2019 to 2022. The prediction task is binary, at risk or not at risk. The model is trained using data from past years and tested on the final year. 10% of the training set is used for validation. Predictions are made at week 3, week 6, and the final week. The model is compared with MLP, RNN, GRU, and a baseline ANN. The ANN model achieved better AUC and accuracy than baseline models such as MLP, GRU, and standard ANN. Its performance was especially strong after 50% of the course, when attention mechanisms could focus on meaningful behaviors. The visualized attention maps matched instructor expectations and provided useful insights. An ablation study confirmed that both time-based and feature-based attention improved model performance. The two models are different in prediction type. The CNN model predicts 4 categories like pass or fail, but the attention model only predicts if a student is at risk or not. They also use different input. CNN uses things like demographics and click behavior, while ATTEN-ANN uses weekly learning activities from Moodle and Bookroll. CNN gives strong results early in the course set, just 20% or 50% progress. Its accuracy can reach 91.8% or even 95%. ATTEN-ANN works best after 50% of the course but it still performs better than all other models tested. The CNN paper didn't report AUC results clearly, but the ATN-ANN model showed much better AUC than MLP, RNN, and GRU. In terms of explainability, CNN is a black box. It's hard to see why it makes a prediction. But ATN-ANN uses attention maps to show which weeks and behaviors are important. CNN is strong at early prediction and handles multi-class problems. Well, ATN-ANN is more explainable and helpful for teachers to take action. The downside of CNN is that it's hard to interpret and slow to respond to changes. ATN-ANN may be weaker at the start and needs good time series data to work well. This project helped me compare two different models, CNN and ATN-ANN. CNN is good at early prediction using time-based learning data, while ATN gives better explainability by showing important weeks and behaviors. It made me realize that both accuracy and interpretability are important in education. In the future, I want to explore hybrid models that combine CNN and attention to build smarter and more transparent tools for teachers. Thank you, everyone.